Okay, chapter 18, day 1. We're going to look at means now. We've looked at proportions. We did confidence intervals for proportions. We did hypothesis testing for proportions. Now we're going to look at confidence intervals for means or averages. So we're working with numerical data that we can calculate an average of. Now, what do we know? We know symbolically that x bar is that average that we get from our data. S, or sometimes has a little x next to it, S is the standard deviation that we have from data, and n is our sample size. So we have to keep that in mind as we go through this. The formula that we're going to use, okay, is, let me just do this. The formula that we're going to use for our confidence interval is our x bar that we get from data, plus minus, just like before, plus minus. Now, instead of a z, we have to use a t for averages, and that's just a rule that we have in statistics. It's a different chart. It's actually one that you've been using. I'm just going to show you how to use it differently. And then times s, which is our standard deviation from the data, divided by the square root of our sample size. This t star with a given number of degrees of freedom, we're going to get from the chart that we usually use, that we've been using for proportions. So, t star we use for means. Why? Because it gives us a more accurate depiction based on our sample size. So one of the things that NAGRA wants you to understand is that the t distribution is just like a z. The only difference is that this distribution will change shape for every different change in sample size. It has n minus 1 degrees of freedom. And so our degrees of freedom formula is n minus 1. It's a calculation we do. But what do I mean by it changes shape? It'll actually change shape depending on the sample size. Now, there's infinite number of sample sizes, so there would be an infinite number of charts, and so that way we don't have that, they reduce it all down to one chart that you've already seen and that we will use. But it's important to know that when n is small, you have very thick tails, and when n is larger, your tails get skinnier, and it becomes more normal, looking like a z-curve. And that's one of the things that NAGRA wanted you folks to understand with t. T looks like z, changes shape for every sample size, and as the sample size gets larger, it looks more like a z-curve. More and more like a z. Okay? So, t star is that critical value now. Instead of z star, we're going to use t star. We're going to use it for our confidence intervals. So we look at our t table. Our t table that we've been using, give me 1 second. This is the t table that we have been using. If you remember from the back of our book, along the bottom we look up our confidence level. For example, 95%, we look here, 1.960. We've already done and used this t-table. The difference is now we have to pay attention to our degree of freedom on the side, which is our sample size, take away 1, is the degree of freedom that we're going to use. So this first part is how do I use this t-table? So for example, if I said I have a problem and my sample size was 28, and I want 90% confidence, I need this t star. Okay? So 90% confidence, sample size of 28. What's my degree of freedom? Well, degrees of freedom is n, 28, minus 1. I know I need 27 degrees of freedom, so I go look at my chart. Degrees of freedom, I need to find 27. There's 27 degrees of freedom, okay? 90% confidence, so that's here. So I come up to 90%, I come over 27 degrees of freedom, and I get 1.6 1.703. So T star 1.703. And if I'm doing a confidence interval, that's the number that goes in place. Instead of like 1.645 or 1.960, we look this up now in the chart based on our degrees of freedom. Let's try another one. Let's say we had a sample size of 310, 98% confidence. So our degrees of freedom is 309. All right, I go look at my chart. 24, 28, 29, 30, 40, 50, 60, 80, 100, 1,000. I don't have 309. So the closest thing I have, and it's not the closest, but it's the next lowest, is 100. Even if the degree of freedom was 900, we would still go backwards to 100. And at 100 and 98% confident, and 100, I am at 2.364. So, what do we know? If the degree of freedom falls between two numbers, use the smaller of those two numbers. So for this chart, which is different than the back of our book, for this chart, we have to use a degree of freedom equal to 100. So a T star for a degree of freedom of 100, because that's for this chart, and it's the chart that you're going to have as well. Again, 100. I come over, 98% confident, I have 2.364. So 2.364. Again, where does that go? In our confidence interval formula, that number goes right here. So we take the mean from our data, times that, or plus or minus that number, times the standard deviation, divided by the square root of sample size. So I have a problem for us to do. This problem deals with leprechauns. I went out on St. Patrick's Day and I measured some leprechauns. I measured 11 leprechauns, and I had an average of 6.41 ounces was a leprechaun. They're not that big. And a standard deviation of 1.36 ounces. So that's data that's given to you in the problem. And I want a 90% confidence interval for the average weight of a leprechaun. All right? So if we go back to our formula here for a second, we know that we are going to need to take the average given to us, plus or minus the T star, that's what we have to look up, times the standard error, which is S over the square root of N. I know what you're thinking. I'm not going to be able to remember that formula. Okay, so let me show you where this formula is going to come from. Confidence intervals from our formula sheet. You're going to have this formula sheet. X bar plus or minus T star S over the square root of N. That is given to you, and it's telling you degrees of freedom is N minus 1. And again, this is means, confidence intervals, one mean. So it is on our formula sheet, so you don't have to memorize that formula. Okay, so there's the formula. So now, degrees of freedom, I have 11 is my N, 11 minus 1. So my degrees of freedom is 10. I have to pay attention to my confidence, 90% confidence, degree of freedom of 10. So let's go to our chart. Degree of freedom of 10, 90% confident. So 90% confident, degree of freedom of 10, 1.812. Degree of freedom of 10, 90% confident, 1.812. So, 1.812. So now that I know that, I can fill in my formula. Again, where do all these numbers come from? Well, that's X bar given in the problem. 1.812, found it from their table. 1.36 was our S given in the problem. And our square root of our sample size of 11. So then I type that on the calculator. Remember, you're just going to do 6.41 plus this number times this. And you can use your phone calculators. And that number minus, and I'm going to get 5.67, 7.15. This is like our lower bound and our upper bound that we would found on the calculator if you did menu 432. But we don't have the calculators. So just type it by hand. Do 6.41 plus this mess, 6.41 minus this whole mess, and you'll get these two answers. So just like proportions, we're going to write a conclusion. So we are 90% confident that, what are we measuring? We wanted a confidence interval for the mean weight of a leprechaun. So confidence that the mean weight of a leprechaun is between 5.67 and 7.15 ounces. And you put your units in. And that's it. You are just taking data that is given to you, plugging it into this formula. You have to look up the t-star though, because it's going to be different for every sample size and percentage. Crank out the calculation, get your two answers, and then just like proportions, write your conclusion. But now we're not talking about percentages, we're talking about, in this case, an average weight, and then our units is ounces, pounds, something, but not percent. And that is chapter 18, confidence intervals for means.